In this chapter, we are going to talk about states of matter and specifically solids, liquids, and gases and how molecules behave based off of those. And we're really going to get into ultimately what is called intermolecular forces, which will define and determine at what temperatures different compounds are solids, liquids, or gases.
The first thing that I want to discuss with you is different types of forces that change properties of different compounds. So molecular forces, we're talking about intermolecular forces. So now between different molecules. And so the three different intermolecular forces that we're going to talk about are dipole-dipole forces. And a subset of those types of forces are hydrogen bonds. We're also going to talk about London dispersion forces, otherwise known as temporary induced dipoles. This is just a different term for that. Ion dipole forces. And so those are the kind of three main types that we're going to discuss in this chapter. So first, again, just to go back to this electronegativity idea, differences in electronegativity for compounds where different things are bonded to each other. For example, fluorine versus boron, if there was an interaction between them, when we have large differences in that electronegativity, the larger that number, the more those electrons within that bond are going to be pulled. So that's why you can see this is kind of a heat map of that system, and you can see that the colors in the diagonals are similar. So the way that I like to do this is, again, to pretend that helium is kind of the center of this stage and then draw lines diagonally down. And this gives us a pretty good estimation of if we're jumping from one line to another in a molecular bond, that we are going to have differences in polarity between those atoms. And there's going to be charges, partial charges that are generated because of that. Remember, we have to look at, even with polar bonds, symmetrical molecules, if there is not a pole, not an end, then they are nonpolar molecules. Asymmetrical molecules, if there are polar, where the dipoles do not cancel out, there's net overall permanent dipoles, which means two ends, right? Di meaning two, poles kind of ends of those. And overall molecular dipoles, they cause molecules to interact. Those changes in where the electrons are causes a different positive charge and a negative charge to build up on different parts of the molecule. And then that allows for those changes in charge to interact with other molecules. Here's an example of a symmetrical molecule where all of those poles cancel each other out. And this is an asymmetrical molecule where we would have, for example, if these were more electronegative, the X atoms, we're going to have a more negative charge over here, a more positive charge on this end. And so this would be a permanent dipole setup in that situation. So we want to look at two different atoms with electronegativity. They're going to be sharing electrons non-equally. So hydrogen and fluoride, if we go back to that other slide, we're talking about two atoms, one with an electronegativity factor that's close to 4 and one that's about 2.2. So this is a lot larger than the hydrogen, which means that there's going to be a large pull of electrons towards that fluorine compared to the hydrogen. And again, this is also still works for this idea because we have to cross three different lines. That gives us a good estimation that there's going to be a large difference in electronegativity, and that hydrogen fluorine bond is going to be a polar bond. One way to show that there are changes in the bond are these little lowercase delta values. So delta is typically a sign that is going to indicate that there is some type of change. And in this instance, right, this is the uppercase delta sign. The lowercase delta sign means that there's a partial change. So there's a partial positive change and a partial negative change. And of course, it's more negative on the fluorine end because it's more electronegative. It's on the further top right side of that periodic table. So it's saying that there's just a partial negative charge here. And so here we have the negative pole and here we have the positive pole. So there are two ends, and this has a bond dipole. Another way that this is sometimes written is that we draw a line and an arrow towards where the negative electrons flow to, and then we put a kind of a line down the middle, dash this, so that kind of looks more positive. It's kind of more of a positive marker on this end. So just two different ways of showing this. So you can see here I am showing that terminology that I showed you just before, where we have kind of the positive end on the left and the negative end on the right. And this negative end is going to be attracted to the positive end of a different molecule. And you can see how we can kind of set up this lattice system where this negative end, negative, and positive, you can align these so that they stack up and they can interact. These are only going to occur between polar molecules, and they need to be close together, and it actually helps pull them closer together because of those differences and changes in charge, that they can have those attractive forces. So the bigger this change, the bigger that the dipole moment, which means the bigger the difference in electronegativities, the more the intermolecular force is increased between these two different atoms. So when we're talking about intermolecular forces, then we're talking about these forces between different molecules. And they're only about 1 to 4% as strong as covalent bonds. Those bonds where, remember, those atoms are close enough to the electron of another atom that they're going to be sharing. So it's not quite as strong, and that's partially because these are not going to get as close. The electrons here are not going to get as close to the nucleus of this atom as the electrons from this atom. So they're a little further away, and that's part of the reasoning for that, but there's still an attractive force there. And you kind of see here that there are generally attractive forces in the green here are going to be greater than the negative forces, so that they have a net attraction to each other. A special type of dipole-dipole interaction that you may have heard before is hydrogen bonding. And it's a really strong dipole-dipole attractive force. It's actually more than that 4% I talked about. It's 10% of a covalent bond. So this is one of the strongest types of intermolecular forces that there are. And they occur between atoms, between hydrogen, oxygen, hydrogen, nitrogen, and hydrogen and fluorine. So I like to say these bonds like to have fun. F-O-N, fun, not F-U-N, fun. So we're going to, if they're attached to one of these different types of molecules, then we can have a big enough change in electronegativity between these elements and hydrogen to give us a really strong polar bond. They're very strong and polar, and they have pretty strong intermolecular forces. Part of the reason for that is if we look at water, for example, you'll see that water is part of that fun group. Remember we have one electron in hydrogen around that proton. And so if electrons are getting pulled towards this oxygen, there's almost a bare proton over here on the hydrogen. That's on that back end. We have a bare hydrogen. And so that positive charge, that allows other things that are negatively charged to get really close to this proton over here. And in that last slide, I mentioned that this strength of the intermolecular force is increased as the distance between them decreases. So the same kind of opposite as this here. So the closer negatively charged things can get to that proton, the stronger that force is. And that's part of the reason that intermolecular force is so strong. Here are examples of hydrogen bonding with water, with ammonia, for example. If we draw out the partial positive and partial negative charges, we can see that the interactions between the partial the elements that are going to be partially negative and partially positive here. Of course, right? Nitrogen's partially negative, partially positive. So we have these interactions throughout this slide showing you those different types of hydrogen bonding. So hydrogen bonding is obviously really important for water. That is the reason it has some of the properties that it does. For example, the hydrogen bonding is responsible for the expansion of water as it freezes, because when we freeze water, they have less energy, and they slow down moving their translational, rotational, and vibrational energies, and they actually form this tetrahedral configuration, and that's what those ice crystals are. When they form ice, they actually are held together by these intermolecular forces, and that's the reason that we have that shape, and they actually get less dense because of it, and that allows ice to float rather than sink to the bottom of our lakes. If ice sank to the bottom of our lakes, there would be no life, because everything would freeze from the bottom up instead of freezing on the top and protecting some of the surface from the cold air. So carbon and hydrogen, you might remember, if we're looking at that chart on looking at kind of the lines through the periodic table, here we have hydrogen and carbon. They're on that same line. So we consider these to be relatively similar in terms of their electronegativity. And so when we look at the slide here that includes hydrocarbons, or hydrogen and carbon in the gray, we can understand that they actually still do have some forces between them. So let's look at neopentane, and we're going to look at the different carbons here that are associated with the molecule. When we have a longer chain of carbon, we can see actually that the boiling point for this smaller molecule is 9.5 degrees Celsius. If it's a longer molecule, the boiling point's 36.1. So boiling point tells us a little bit about how these things hold together. When something boils, it goes from a liquid to a gas. And the reason it's a liquid is because those intermolecular forces are holding that content, that material, together. And if we give it enough energy, it's going to be able to boil, which means that it releases itself from the liquid and turns into a gas. So these shorter elements have a different boiling point as the longer elements, and this suggests that even though this isn't a polar molecule, that there are some other types of bonding that are involved. And these are called London dispersion forces, otherwise known as temporary induced dipole. So these electrons, remember, in these, let's say this is a circular cloud of electrons, right? An electron density. And they're kind of random in where they're going to be, but at any given time, the electron density can be heavier on one side than the other. And so this temporary induced dipole, just because of where these electrons happen to be, can actually interact with other different types of electron clouds next to it in an adjacent molecule, and that can induce a dipole as well. And those changes, those temporary inductions of different dipoles, allow for these interactions to occur. Here's another image kind of representing the changes in the electron cloud. And let's start here in the kind of the middle, where you'd have an even distribution of the electrons. And then all of a sudden, maybe you have one kind of flowing. You have this one decides that there's going to be more electrons over here temporarily, and that repels the electrons. And those changes in those different cloud amounts will help to generate interactions between these different molecules. So the larger the molecule is, so the further you go down the periodic table, right, the larger those shells are of the electron clouds, the more polarizable they're able to be. So again, and the larger the number of less tightly held electrons, that's the same thing as going down the periodic table in those different shells. And then you can generate bigger changes of that charge. So you can see a smaller molecule already, have smaller charges building up here. but you have a really large shell, you're able to kind of get that polarizability is larger, and the magnitude of that partial charge is larger. Looking at some data that supports that hypothesis and idea, if we have looking at the halogens, for example, as we go from the top of the periodic table down to the bottom, we can see that boiling point increases dramatically from negative 188 degrees Celsius to positive 180 degrees Celsius for iodine, molecular iodine. So we can see that that changes due to that change in the size that we talked about here. This would be representative of fluorine, for example, versus iodine. And these changes in that London dispersion force is going to change their boiling point. So this is an example of looking at London dispersion forces and the number of atoms involved. So we go from methane, ethane, propane, butane. So we get larger. You can see the number of carbons is increasing. And we go from negative 161 to 0.5 for butane and degrees Celsius. So this is looking at, and then when we get to 22 carbons, the boiling point's up to 327 degrees Celsius. So huge changes just by adding longer chains of carbon. These London dispersion forces are actually how, if you've ever seen a gecko climb up a wall, or some different types of animals are able to kind of stick and climb in weird places. Part of the reason is because they have big, huge, long pads on their feet that are very fatty, that have a lot of hydrocarbons on them, essentially. And if you zoom in, you can kind of see these pads. There's a lot of surface area and a lot of points where you can have those temporary induced dipoles sticking on whatever surface they're trying to stick onto. And so there are a lot of number of points of attraction. They're very polarizable chains of hydrocarbons, and so it allows a very sticky kind of foot due to that. Even though individually those London dispersion forces might not have that big of a magnitude, if you add them all up and you create a lot of them, then they can actually generate a decent amount of hold and stick that obviously allows a gecko, for example, to walk up a wall or across a ceiling. Okay, so based on that idea, which of these molecules would have a higher boiling point? And what intermolecular force is responsible for this? Remember, usually we have this system where these darker gray carbons are darker gray molecules. The darker gray atoms here in here are carbon, and the white versions are hydrogen, and the same over here. The longer one is going to have a higher boiling point, and London dispersion forces is the reason that they have higher boiling points. Different type of intermolecular force is ion dipole. So we talked about water as one type of dipole, right? Here's the oxygen, two hydrogens here. We have that bent shape because we have the lone pairs of electrons on the top. Partial negative charge on the oxygen, partial positive charges on the hydrogens. And if we have an ion, for example, a sodium ion, a positively charged Na+, so let's give that Na+, and over here we have a Cl-, right? These different dipoles, these partial negative charges, are going to be attracted to that full positive charge. And so we're going to have the ability to interact with these different ions. And so this is what actually allows sodium and chloride or salt to be dissolved in water. If something's dissolved in a different solvent, that means that it's completely surrounded by the solvent molecules, and in this case, water. So ions are able to be dissolved because of this ion dipole attractive force. Another example of aluminum ion is being attracted by the partial negative forces of the water molecules that are shown here. And you can see that these are going to surround this and allow it to be solubilized. This type of interaction is quite strong because it's not a temporary interaction. This is a permanent charge here. And so there's going to be a pretty strong intermolecular force between the normal dipole molecule and that permanent ionic charge. So in summary, for the intermolecular forces, we have dipole-dipole interactions that are going to occur between neutral molecules with permanent dipoles. Remember, we have to look at electronegativity. We're going to look at electronegativity between the atoms of those molecules. And if they have differences that are large enough, and again, I would recommend looking at elements that are bonded in between those different lines I mentioned earlier. That's going to help us determine if there is a dipole-dipole polar bond. About 1 to 4% of a covalent bond in the middle of the road in terms of intermolecular force strength. Hydrogen bonding is a specific and a special type of intermolecular force when it's attached to FO or N, and this is about 10%, so it's a little stronger, one of the stronger intermolecular forces. And again, it has to be a hydrogen attached to FO or N. We spoke about London dispersion forces, and they're present in all substances, but it's one of the weaker intermolecular forces. You can add them up to large net attractive forces if you can get things to line up and be really close to each other to induce those temporary dipoles. We also have ionic dipole interactions, where ions are attracted to polar molecules. And this because that ion charge is permanent, and polar molecules have kind of this permanent dipole setup as well. This is actually one of the strongest intermolecular attractive forces of the ones we have discussed. And we didn't really talk much about this, but there is the ion-induced dipole. It's kind of the mix between London dispersion and ion dipole. If you have really big atoms that have really large clouds that are really far away because they're further down the periodic table, we can sometimes, due to ions having that permanent charge, you can induce dipoles on neighboring particles due to that. And again, it mostly has to do with how large that atom is, or that molecule is that you're looking at. All right, here's a quick quiz question. Pause it, do this. If you can't figure it out, then I would recommend kind of rewinding and watching some of the previous slides. So usually understanding these intermolecular forces helps us to be able to predict some of those properties of the different types of molecules and which intermolecular forces are available to it. The stronger the intermolecular force and the more spaces that it can interact, obviously the higher the boiling point and the more it's going to be able to interact in terms of a solvent or being miscible in each other. All right, here's another quick kind of little quiz question in terms of listing all of the intermolecular forces for ethanol. And please, if you can't determine that, then I would kind of rewind and see if you have missed any. So this is the methanol structure, and you should be able to, just based off of that, figure out which of these 5 questions would be correct. All right, so in terms of which species has the strongest intermolecular forces here, methane, molecular chlorine, molecular oxygen, or hydrogen fluoride. And in this case, hydrogen fluoride is the only molecule that has a difference in the electronegativity between these two. So if we go back to that periodic table where we put the lines through it, we know that carbon and hydrogen are on that same line. Chlorine and chlorine are obviously on the same line. Oxygen and oxygen, they're going to equally share electrons. This is going to have a partial positive and a partial negative, and also it's one of the FON, so this is going to be hydrogen bonding capacity. So this will have the highest and the strongest intermolecular forces. The intermolecular forces also have something to do with solubility. So if things have high intermolecular forces with each other, they're going to be able to be soluble in each other. And so we're looking at polar substances, so things that have those dipoles that are permanent, those are going to be able to be solubilized in a polar solvent like water, for example. Non-polar substances are things that don't have those dipoles. You are not going to be very water soluble, for example, because their water would rather interact with water rather than oil, for example. So comparing the relative polarity of those compounds is going to help us determine if something's going to be soluble or not. There's some really interesting chemistry that happens with surfactants. So things that if you want to add pesticides to plants, for example, there are a lot of times different plants will have kind of this waxy coat on top of it. But if you want to add a pesticide, it's not helpful if it just falls off the leaf. So there are things that you can add. Surfactants, for example, can help allow that water to kind of mix with the pesticide, for example, and stick onto the plant leaf. So it's kind of the same idea as soap, right? If you have greasy, oily hands and you use soap, that helps to pull off the grease. Or if you're doing the dishes, that soap helps to kind of mix with the water and the oil at the same time. So there are things that you can add that have properties of both that help those kind of differences in intermolecular forces kind of be able to be combined on a single type of molecule. This idea of mixing these different properties together is also how we move fat around in our bodies. For example, chylomicrons, we have polar head groups on the top part of this. There are polar molecules, and like we looked at the triglycerides in the lab the other day, there are oftentimes these long tails of hydrocarbon. So we can kind of get fat and cholesterol within our bodies, and we can move them in these little packets that where we kind of have the polar head groups are going to be attached on the outside and non-polar groups are going to go on the middle. And so that's just another mechanism that is used in chemistry to understand how things are transported even within the human body. So I want you to think about which of these following three compounds are not expected to be soluble in water, and why is that? Okay, so in this one, we're looking at potassium iodide. What intermolecular attraction is allowing that to dissolve in water? So please pause if you don't know the answer, rewind and head back. In this one here, I'd like you to pause and think about which of these has London dispersion forces as its strongest intermolecular force. I'm going to actually walk through this one because it's a bit of a trick question. If we look at methane, we know that the difference in electronegativity between carbon and hydrogen is pretty minimal. And so these are going to be, and it's a tetrahedral shape, so there's no polarity. So that means that London dispersion is going to be really the only intermolecular force at play here. CO2, you might say, oh, that's oxygen and carbon. But remember, CO2 has this linear shape, and we have partial positive, partial negative forces, but there are no dipoles here. So we're not going to have the dipole interactions as an option here. So that is not going to be one. That means that the London dispersion forces are really the only forces that are going to be at play there as well. And oxygen, we know, is going to have the same issue. There's no changes because they're the same type of atom, so there are not going to be differences in electronegativity. So London dispersion forces are also really the only option there as well. A few more properties that can be explained by these intermolecular forces, and one includes surface tension. So you've seen water bugs kind of running across water. And part of the reason is because there aren't intermolecular forces that are pulling that water together. And so in order for a bug's foot to kind of go through that water, you have to break that surface tension, which is the force between those two different molecules. So there are here they allow us to have surface tension on the water, and this can be measured in the lab, looking at kind of the angles that these different water droplets, for example, are going to form on top of a waxed car. For example, you'll notice that it beads up really nicely versus kind of sucking down onto the surface. So that's the difference between surface tension, and you can kind of get an idea between if those things are going to be nonpolar or polar, for example. So here's another image that's pretty interesting. We can look at silicon oxide, which is glass. And glass is actually between silicon and oxygen. These are really polar forces, right? The oxygen is going to be pulling a lot of negative charge away from the silicon. And so you can see here, if I put a bead of water, it will kind of stick down and it'll kind of cover and spread out really well here. So that intermolecular forces are going to be pulling that water towards it. If I put a layer of grease on top, so that's this kind of purpley layer here, and you can kind of see that there's a layer of grease put on, that water doesn't suck down anymore because there aren't the same type of intermolecular forces, so that water beads up. So that's the same idea as that previous slide here, where we're looking at the hydrophilic versus hydrophobic sides here. And it's a bit of a misnomer. It's not that grease is scared, or that's what the phobic means, right? It's not that the grease is scared of it. It's just more that the water would rather be attracted to itself. It's the same as the surface tension idea. The water likes to be with itself, so it's just able to make more interactions in this shape with itself than it would be in this shape, right? So it's not that that grease is afraid of water. It's just that water is going to generate. It has the stronger intermolecular force, so it's going to form as many of those bonds as it can. In order to break that surface tension or break those intermolecular forces between molecules in a certain solvent like water, sometimes we use things such as surfactants, otherwise known as detergents or soaps. And this is what that broken down soap, when we looked at that lab, this is what it looks like after we've broken it apart from the triglyceride. So this is a long hydrocarbon chain, so hydrogen and carbons along each of these points. And then we have a polar tail because we have oxygen connected to a carbon, which oxygen is more electronegative. So electrons will be pulled out. These will be kind of more negative ends that can then interact with the through hydrogen bonding with water. The water will be doing the hydrogen bonding here, and the sodium can interact with the partial negative charge on the oxygen. There are different types of head groups here that you can see, various different types of polar groups on the end, and it allows these ends to interact with water and dissolve within water, and also allows greases or other oils or nonpolar things to interact with these tails through London dispersion forces. Another type of property that is involved and that utilizes these intermolecular forces is viscosity. So you can think of the different types of flow for different types of fluids. For example, if we look at the difference between water is pretty non-viscous substance. It'll drop off easily from a spoon, for example. Milk be a little thicker, oil thicker yet, and then we get all the way up to syrups and chocolate might be really gooey, and it might kind of hang down longer. So that it won't go through, for example, a straw as easily. It'll take longer in your pipette. It'll get stuck in there. So these are all based on intermolecular forces. So the stronger the intermolecular force bonds, the more sticky it is going to be with itself. So if we're looking at the intermolecular interactions that can happen between, for example, ethylene glycol and acetone, we know that acetone has polar bonds, but there's no hydrogen bonding because this oxygen doesn't have a hydrogen attached to it. So this acetone, we would say, cannot hydrogen bond. Ethylene glycol, on the other hand, with itself, right, it can hydrogen bond because it has oxygen attached to hydrogen on both ends. So ethylene glycol is a really sticky, viscous substance because it has two areas where it can interact and grab onto itself. For example, here, if I've drawn out, you can see that there could be maybe interactions with hydrogen oxygen on one side, and depending on the orientation of this other hydrogen, we can also interact on both sides. So it can be really sticky, and we can create these chains of this via hydrogen bonding interactions. Over here, not only does ethylene glycol have hydrogen bonding, but also just regular dipole-dipole interactions and London forces. So all three of those types of interactions. Remember, hydrogen bonding is just a subset of dipole-dipole. And every different molecule is allowed to have London forces with other molecules. So the acetone has a dipole because it's carbon and oxygen. There's a difference in electronegativity. And then there are also London forces, but the big one is the hydrogen bonding.
Those are the intermolecular forces that are going to dictate if things are in solid, liquid, or gas form. I was mostly talking about liquid here, and I'm going to make another quick video that will kind of finish up chapter 8, kind of talking about gases and their interaction with each other.